Have you ever looked at a circuit diagram and just felt your brain start to melt? Wires going everywhere, multiple batteries, and you're just thinking, where do I even begin? Well, today we're going to unlock the secret with two beautifully simple but incredibly powerful principles: Kirchhoff's rules. These are the absolute keys to analyzing any electrical circuit, no matter how much of a tangled mess it looks.
So here's our game plan. First, we'll see why the old standbys, like Ohm's law, sometimes just don't cut it. Then, we're going to meet our two new best friends, the junction rule, which handles current, and the loop rule, which takes care of voltage. After that, we'll roll up our sleeves and put them to the test on a real circuit. By the end, you're going to have a complete toolkit for cracking any circuit. Sound good? Let's dive in. All right, first things first. You might be wondering, hang on, why do we even need new rules? I mean, what's wrong with the basics we already know, like Ohm's law or the formulas for adding up resistors in series and parallel? Well, the short answer is, those tools are great, but they have their limits. They really only work for, simple circuits. The moment you run into components that aren't clearly in series or clearly in parallel with each other, those methods kind of fall apart. You need something more fundamental, something a bit more heavy-duty. Just take a look at this circuit, for instance. It's got multiple power sources and this whole web of resistors. Now, you might be tempted to say, oh, I'll just combine that 40 ohm and 20 ohm resistor. But nope, you can't. The current has all these other paths it can take through those middle wires, creating these interconnected loops. And that's exactly where our standard bag of tricks fails us. So we need to bring in the big guns, starting with Kirchhoff's first rule. To crack these kinds of puzzles, we're going to lean on the genius of a 19th century physicist, Gustav Kirchhoff. His first rule is super intuitive. It's basically all about what happens when the current gets to a fork in the road. This is what we call Kirchhoff's current law, or KCL for short, and it applies to any junction in a circuit, which is really just a fancy word for any point where three or more wires meet up. The rule itself, it's beautifully simple, and it comes right from one of the cornerstones of physics, the conservation of charge. You can't just create or destroy electric charge out of thin air, right? So whatever current flows into a junction has to be the same amount that flows out. The fancy math way of saying this is that the sum of all the currents at a junction is zero. By convention, we just say currents going in are positive and currents leaving are negative. But honestly, the best way to think about it is like water in a set of pipes. If you have 10 gallons of water per minute flowing into an intersection, you have to have exactly 10 gallons per minute flowing out through the other pipes. It can't just poof, vanish. It's a perfect balancing act. What goes in must come out. Okay, so the junction rule takes care of the flow of charge. That's one huge piece of the puzzle. But what about the energy in the circuit? Well, for that, we need the second part of our toolkit, and it's just as powerful. It's called the loop rule. This one's known as Kirchhoff's voltage law, or KVL. And if KCL was about conservation of charge, KVL is all about the conservation of energy. And it's a really cool idea. Basically, it says that if you pick any point in a closed loop in a circuit, and you go for a little walk all the way around that loop until you get back to your starting point, the total change in voltage has to be zero. Again, the formula is super straightforward. The sum of all the voltage changes around the loop equals zero. And I love this analogy for it. Think about going on a hike. You start at your campsite, you climb up a huge mountain, go down into a valley, and then hike all the way back to your original campsite. When you get back, what's your net change in elevation? It's zero. You're right back where you started. The loop rule is just the electrical version of that exact same journey. All right, enough theory. We've got our two essential tools, the junction rule for current and the loop rule for voltage. Now, let's get our hands dirty and actually put them to work on a real circuit from our source material. Let's solve something. So here it is. This is our challenge. We've got this network with two different batteries and a handful of resistors. And notice, just like we talked about, nothing is in a simple series or parallel arrangement. Our mission, should we choose to accept it, is to find the exact current flowing through every single branch of the circuit. And we're going to follow a really clear step-by-step process. First, we assign variables to the unknown currents, using the junction rule to do it efficiently. Second, we'll trace those hikes around the circuit loops to create our equations using the loop rule. And finally, step 3, we just solve the system of equations. That's the whole plan. Now, if you look closely at the diagram, step 1 is actually already done for us, which is pretty handy. See those labels? At junction C, you've got current I3 flowing in from the top and I2 flowing in from the left. Remember our rule? What goes in must come out. So the current leaving through that middle branch must be the sum of the two, or I2 plus I3.
Applying this logic everywhere is a really slick trick to minimize the number of variables we have to solve for later.
Okay, on to step 2, applying the loop rule. This is where the magic really happens. By tracing a path around 3 different closed loops, like that top left one, A, D, C, A, and adding up all the voltage gains from batteries and subtracting the voltage drops across resistors, we set the total to 0. Doing this for 3 unique loops gives us this system of 3 distinct linear equations. We've officially translated a tricky physics problem into a totally solvable algebra problem.
And now, step 3. We solve. We take those 3 equations for our 3 unknowns. Now don't worry, I'm not going to walk you through all the nitty-gritty algebra, but the solution gives us these precise values for I1, I2, and I3. And here's the beautiful part. Once we have these, we know everything. We can find the current in any branch. For example, the current in that branch AB is just I1, or 2.5 amps. The circuit is completely solved.
And there you have it, a powerful, systematic method for taming any complex circuit. So let's just do a quick recap of the 2 fundamental rules that make up your new circuit-solving toolkit.
This really brings it all together. On one hand, you've got the junction rule. It's based on conservation of charge, and the analogy is simple: water and pipes. What flows in must flow out. On the other hand, you've got the loop rule, which is all about conservation of energy. And that's our round-trip hike. You always end up back where you began. These 2 principles are fundamental to how the universe works, and together they give us a complete picture of any circuit.
So the next time you see a circuit that looks like an impossible maze, you'll know exactly what to do. You've got the rules, you've got the method. The only question left is, what problem will you solve first? Thanks for joining this explainer.